Okay, last section of chapter 11 is Lagrange multipliers. This is another method for optimization problems. We can definitely use the methods in 11.7, but 11.8 methods with these Lagrange multipliers are going to be a little bit quicker. They will definitely test your algebra skills and just solving multiple equations. There's some examples where you might have 5 equations with 5 unknowns, and you have to get kind of creative with your substituting, and it can be very fun and it can be very frustrating. So we'll go through some of those examples. I would strongly encourage you to definitely look at the examples in the book, to look at some of the strategies that they use. And beyond that, look at some of the extra homework problems in the book, not just the ones that are assigned, but some of the other ones. So just kind of pick up on some of the kind of advanced techniques of solving these that you can get to. But let's start here with a little idea. Bring you back to Calc 1. A rectangular box without a lid is to be made of 12 square meters of cardboard. Find the maximum volume. Okay, so we could get this started. Your intuition could probably take you in the right direction here, where we would say something like, well, volume would be length times width times height. Remember your primary equation, the one that you want to maximize or minimize. And then your secondary equation, if you remember that, we called that in Calc 1, this was your primary. That's to be optimized. And then your secondary that gave you a little bit more information, so we have that 12 meters squared for our surface area, which would be, there's no top, so just length times width plus 2 length times height plus 2 width times height. And that had to equal 12. Okay, so that was your secondary equation. And remember, that gave you that extra information. Okay. If you remember, the next step is to solve your secondary for one of the variables, plug it into your primary, differentiate, and solve. Okay, the problem that we have here is that there's too many variables. Okay, so if you remember in Calc, you were given another value here. So you would say something like the height had to be, 1 meter or whatever. We've got too many variables to do this the Calc 1 way. So what you guys just learned for Calc 2 is that we can solve this for one variable. Let's solve it for h. We would have 12 minus LW. And then our h's would be on one side, and we could divide by 2L plus 2W. Okay, so that's your secondary equation solved for h. So then V equals LW times 12 minus LW over 2L plus 2W. Okay, but again, there's too many variables for us to do like dVdL or dVdW like we would have done in Calc 1, but we do know now that we can do this with partials in Calc 3. So I'm going to distribute that LW. Okay, and then we can do dVdL, which doing your low, d high, minus high, d low, all over little squared. Okay, and we can simplify some stuff out here. We'd have 24 LW minus 4w squared L squared plus 24w squared minus 4w cubed L minus 24LW plus 2L squared W squared, 2L plus 2W squared. So we got some that cancel out here. So we'd have negative 4W squared L squared plus 2W squared, so negative 2W squared L squared plus 24W squared minus 4W cubed L. You can factor out a 2W squared. 2 oops. And in fact, we could factor since the bottom, is being squared, we could factor a 4 out of there, right? So we could do, this would be 4 times L plus W squared. Okay, so you can simplify it all the way down to dV dL would be W squared times negative L squared plus 12 minus 2WL over 2L plus W squared. Okay, and again, W is treated the same way in that equation, so dV dW, we would just swap our variables. Okay, and then remember we figure out what would make both of them 0. Obviously, if W were 0 or L were 0, that would work, but remember that's your trivial solution. That's going to give you the minimum volume. We want the maximum volume. Okay, so if we could do that negative L squared plus 12 minus 2WL equals 0. So L squared plus 2WL equals 12. And then we get our second one over here. If we plug it in, let's see, let's solve this one for, what do we want to solve it for? Well, maybe we could solve it for 2WL. Okay, so then we plug it into our second one. If L squared times negative W squared plus 12 minus 2WL equals 0, then L squared times negative W squared plus 12 minus 12 plus L squared, and I'm just subbing this in for 2WL, equals 0. So L squared times negative W squared plus L squared would equal 0. Okay, and that would work again if L squared were 0, which they can't. That'll give us it can, but that would be the minimum volume. Or if W squared equals L squared. Okay, so we've got that W equals L. Okay, well, then we can go back to this guy right here. If W equals L, see, we got a lot of algebra going on, right? L squared plus 2L squared equals 12. So 3L squared equals 12. L squared equals 4. So L would be 2, not negative 2, right? Because it's a box. Length has to be positive. And that would mean then that W also equals 2. And then our height, with that height formula above, 12 minus LW over 2L plus 2W, which would be 12 minus 4 over 4 plus 4, which would be 8 over 8, which is 1. Okay, so H is 1, and then the maximum volume would be 4. Okay, and we learned that in the last section. Okay, that's something that we could do. And it wasn't awful, right? It looks kind of awful, but it wasn't awful. Just solving this system of equations where this guy equals 0 and I didn't rewrite the original one. Negative w squared plus, well, hold on. This guy, I wrote it right here. What am I doing? This would equal 0. Okay. And we got it. Okay. Now we're going to talk about another method of doing that. So we're going to look at kind of a different idea here where f of x is your primary, okay, and g of xy is your secondary. Okay, so think about level curves. Okay, so if f of xy, that's what we're trying to maximize or minimize. So k could be different values of f of xy. And we could kind of draw in like some level curves for k. Okay, so maybe this is k1, k2, k3, k4. Okay. And let's say, what do I want to do here? I'm going to say k1 is the biggest one. So k1, I'll write it down here. K1 is greater than K2, which is greater than K3, which is greater than K4. So in a maximization problem, ideally we could be on the K1 curve. Okay, we're going to try to get the highest value we can. But then we've got this restraint going through. Okay, and let's say your restraint curve, and K doesn't necessarily have to be a whole number. Okay, so let's say that your restraint curve goes through like that. Okay, so this is g of xy equals some constant. That restraint is set. Okay, so you can see the biggest we can get is right here on K2. Okay, with that restraint, we cannot obtain K1. Okay, let's say this is at the point x naught, y naught. Okay, so there's our constraint. So our maximum value would be K2, and that will occur at x naught, y naught. Okay, we can obtain anything less than K2. Like we can obtain K3 if we want, but we wouldn't want to do that. Okay, and there's no way for us to get higher than K2. And then like I was saying before, maybe, and I'm going to erase this in a second, maybe your constraint curve looks like this. Okay, well, then you just got to think about the level curve that would fit right in here and would be, maybe more like that. Okay. But there's going to be some place where they just hit each other like that. Okay. Your constraint curve just butts right up to your level curves for your function and shows you the maximum value that you can have. And what happens there, it's very handy, is that they share a tangent line there. Okay, which means that they share a normal line there, right? If they have the same tangent line there at that point, the geometric, that's just how it happens. That's just how your constraint will intersect your level curves, and there will be a tangent line there. Okay, which means then that the normal line would be the same. And what we just learned is that normal line that moves through those level curves is the gradient. Okay, so they have the same gradient vector direction. So we're going to have the gradient of fxy, I'm going to do it at that point, is some scalar multiple of the gradient of g. Okay, and that's just this really kind of amazing relationship that exists there and allows you to solve a problem like this. This scalar that we draw, that's lambda. I'm gonna make sure I spelled it right. Something lambda. That's right. I'm thinking there's no B in there. Nice. I'm thinking like the animal. Lambda. that is your Lagrange multiplier. Okay. And so back to our warm-up, or our opening problem that we had there, where f of xy was your volume, okay, and g of xy, was your constraint, which was that 12 equals 2LH plus 2WH plus LW. I don't know if I like the notation that I'm choosing here, but there we go. So we have our primary and our secondary. It's really easy to take our gradients. Just when there's LW and H, you want to say X would be L, Y would be W, and Z would be H, or just switch it to X, Y, and Z. It doesn't really matter, okay? So the gradient of F is going to be WH, LH, LW. The gradient of G is going to be 2H plus W. Oops, I don't know why I wrote L. I said H. And then 2H plus L. And then 2L plus 2W. Okay. So now we put together this system of equations. The gradient of F is lambda times the gradient of G. So WH is lambda times 2H plus W. LH is lambda times 2H plus L. And LW is lambda times 2L plus 2W. We do have 4 unknowns. We don't know L, H, W, or lambda. We do have a fourth equation, and that's your secondary. 12 equals 2LH plus 2WH plus LW. Okay, so we have 4 equations. 4 equations, 4 unknowns. We can solve for them. We don't ever have to solve for lambda, okay? We do need to be able to figure out what the maximum volume is. So we do need length, width, and height, okay? So there's different ways you can solve this. I believe this is done in the book, and you could take a look. They kind of use a strategy of making them all, so left-hand side is length times width times height, which is interesting. I'll show you another way. I'm going to label these. Let's see, I'm going to actually move this. Okay, and then I'm going to expand these just a little bit. So 2 lambda h plus lambda w, 2 lambda h plus lambda l, 2 lambda l plus 2 lambda w. Okay, so this is kind of the fun but tricky part. We need to solve. However you want to solve algebraically, what I'm going to do is take the second equation, okay, and solved it for 2 lambda h so that I can plug it into the first one. So in the second equation, 2 lambda h equals LH minus lambda L. Okay, again, I took the second equation, rearranged it so I solved it for 2 lambda h so I can plug it into the first one. So then in the first equation, WH equals LH minus lambda L plus lambda W. Okay, so now this is where it gets a little tricky. You got to try to figure out maybe some grouping that you can do. Oops, H minus lambda. Okay, so I kind of spotted that h minus lambda there. And you might have to try a few things till you figure out a good way to rearrange that works. But I got that the width would have to equal the length. Okay. Now I'm going to take the third equation, and I'm going to solve it for L. What did I do here? I'm going to solve it for L lambda. Is that what I wanted to do? I'm going to take the second one and solve it for L lambda. See, even I have it all written down. Okay, so for the second one, I'm going to solve it for that L lambda so I can plug it into the third one. Okay, so in the second one, L lambda equals LH minus 2 lambda H. And I'm going to plug it into the third one so that LW equals 2 LH minus 2 lambda H plus 2 W lambda. Okay, so LW 2LH minus 4 lambda H plus 2W lambda. And then what I'm going to do here is I've already solved that W has to equal L. So L squared equals 2LH minus 4 lambda H plus 2 L lambda. L squared minus 2L lambda equals 2LH minus 4 lambda H. And I can factor out an L, and I'm left with L minus 2 lambda. And I can factor out a 2H. I'm left with L minus 2 lambda. So L equals 2H. Okay, and again, you might see that and be like, how did you know to do that? And it wasn't super obvious right away. I tried a few things until I figured out something that would work. Okay, there's no step-by-step here. I can't tell you like you need to solve equation 2 for this variable and then plug it into equation 3 and then do this step and this step. And there's no step-by-step here. It's just you are in Calc 3 now. Here's 4 equations with 4 unknowns. Try to solve it. Okay, it's not always super easy. Okay, but now we have our fourth equation that is 12 equals 2LH plus 2WH plus LW, and we can sub these out. We can maybe change, let's do it all, swap out, so everything's in terms of H. 12 equals 2 times 2H times H plus 2 times, if W equals L and L equals 2H, W also equals 2H. Okay, so we get that 12 is 4H squared plus 4H squared plus 4H squared. So 12 is 12H squared. So 1 is H squared. So H is 1. And then W and L are both 2H. So the volume again is 4. Okay, so that's how we just solved that same problem using 11-7 methods and now using Lagrange multipliers. Okay, I'll do 2. You know what? I've got 3 more examples to do. So if you want to kind of pay attention, I'm going to do another one that's a little bit more straightforward, I think. Then I'm going to do one that has 2 constraints to it. And then I'm actually going to do the one that we did in the 11-7 video. What was that one? That was the box fitting inside of a sphere. So I'm going to do 3 more examples. One will be another kind of more straightforward one. One will be one with 2 restraints, and then I'm going to revisit the one that we did in the 11-7 video, and we're going to do it with the Lagrange multiplier way. Okay? I would encourage you to kind of like pause as we go and try to see if you can figure out the next step on your own. Now let's go here. So next example. We are going to maximize the surface area of a cylinder. So surface area of a cylinder would be 2 pi r squared plus 2 pi r h. Okay, and the volume has to be 100. Okay, so again, we're maximizing surface area. That's our primary, with the constraint that the volume has to be 100. Okay, so we're going to call that, remember, this is your F and this is your G. Okay, so the gradient of F. And we're going to want to have like X is going to be, let's do X is R and Y is H. Okay, so we're going to have 4 pi R plus 2 pi H, and then 2 pi R. And then for G, we're going to have, and remember that 100, technically these should be set equal to 0, but it doesn't really matter. Any constant is just going to be 0 when you take the derivative anyways. So then we're going to have 2 pi RH and pi R squared. Okay. So first step, we take the gradients. Next step, we get our system of equations. 4 pi R plus 2 pi H will equal lambda 2 pi RH. 2 pi R will equal lambda pi R squared. Okay, and then 100 is pi R squared H. So we have 3 equations and 3 unknowns. And this one is going to be pretty straightforward. You might get to some other ones where there's more than one possible answer for like lambda or, well, not so much the R's and the H's, but I think we'll probably have to visit those as they pop up in the homework. I wouldn't worry too much about them now. Basically, you don't, like lambda would never equal 0 when you're solving for these. In these application ones, the radius and height shouldn't ever equal 0. But yeah, let's go here. So yeah, I was just looking at, if you look at this one, like you could say, well, if lambda is 1, then 2 pi R would have to equal pi R squared. And then you get that R is 2. And like you end up with, that doesn't work. There's no solution there. I'm not going to get too far ahead here, but you might see some in the homework. I didn't mean to just confuse you there. Sometimes my brain gets ahead of what I'm going to do here. Okay, let's keep going. All right, so these aren't too bad to solve. Okay, we can simplify them a little bit here. Like in this one, we can take out all the 2 pi's, right? So 2R plus H equals lambda RH. The second one, we can take out a pi and an R. So 2 is lambda R. Okay, and then we still have the 100 is pi R squared H. Let's see here, like for this one, we can do then R is, what do I want to do here? Maybe do lambda is 2 over R. And then I can plug it into that guy. So then I'm going to have 2R plus H equals 2 over R times H. So 2R plus H is 2H. Okay, and then we get R, 2R is H. Okay, that's a good little relationship there, because then we can plug that into our third one. 100 equals pi R squared times 2R. So 50 is pi R cubed. 50 over pi is R cubed. So R is the cube root of 50 over pi. And then H would be 2 cube root of 50 over pi. Oops, pi. And we're trying to maximize the surface area. I don't think this one explicitly asked for us to go that far. I think it just said the dimensions that would maximize it, but the surface area then would be 2 pi 50 over pi to the 2/3. 2 pi r squared plus 2 pi r, 2 pi r h. So 2 pi, I'm going to get the 2 from the h, and then that would be 50 over pi to the 2/3. So we'd have 4 pi, so it'd be 6 pi, 50 over pi to the 2/3. Okay, you could use your calculator to get the decimal for that, but there you go. All right, so that's a pretty good straightforward example. Next one, I'm going to do one with 2 constraint equations. And that doesn't, you just have another Lagrange multiplier in it. You have another unknown. They can get a little bit tricky. This one, we're not going to have a context to it. We're just going to say f is, 3x minus y minus 3z. And then we're going to have our constraints that x plus y minus z has to equal 0, and x squared plus 2z squared has to equal 1. Okay, our gradient of f would be 3, make this pretty easy for you, -1, -3. And then I can make any of them too tricky. Gradient of g would be 1, 1, -1. And then we're going to call this guy h. So that would be 2x, 0, 4z. Okay. So now you would do the gradient in f is lambda times the gradient in g plus mu. They just throw in another variable to use. Okay. So then 3 would equal lambda plus mu 2x. -1 would equal lambda. That helps. -3 equals negative lambda plus 4zu, or mu, I'm sorry. I'll put the mu in front. Okay, and then we have our other constraints. X plus y minus z has to equal 0. X squared plus 2z squared equals 1. So we've got a system of 5 equations with 5 unknowns. We've got x, y, z, lambda, and mu. Okay, well, good news is lambda is -1. Okay, so now we can actually rewrite these knowing what we know. That means that 3 is -1 plus mu 2x. 4 is mu 2x. Okay, and then we would have -3, this one, -3 equals 1. So I'm going to just go ahead right away and do -4 equals mu 4z. Okay, and then we've got our other one still, excuse me. X plus y minus z equals 0, and our x squared plus 2z squared equals 1. Okay, well, you can kind of see here that we're going to be able to get a relationship between x and z, right? We can get from this one that x would equal 2 over mu. Okay, and we can get from, I'm doing a little different than I did in my notes, I guess. I am going to do it a little different. Okay. Here, well, what do I want to do? I'm going to do mu equals 2 over x from the first one, and mu equals -1 over z. So if 2 over x equals -1 over z, then 2z is negative x. Okay. So then I can plug that into either of them. Let me just make sure that I got 2z is negative x. Yeah, okay. So I got a relationship between x and z, which is great because now I can use that last equation. So 2z is negative x, so x is negative 2z. So negative 2z squared plus 2z squared equals 1. So 4z squared plus 2z squared equals 1. So 6z squared equals 1. Z squared would be 1/6. Z could be positive or negative 1/6. Okay? So if z is positive 1/6, then x is negative 2z. So, oops, and I forgot to square root it. Square root. Okay. And so that is, I'm just going to square root the top. Right? We can simplify that to 1 over the square root of 6. If z is 1 over the square root of 6, x is negative 2 times z, so negative 2 over the square root of 6. And if z is negative 1 over the square root of 6, then x is positive 2 over the square root of 6. Okay, and then we can use this equation to get what z would be. Z is x plus y. So, I'm sorry, we gotta get what y is. Y would be z minus x. Okay, so in this one, y would be z minus x, so 3 over the square root of 6. And for this one, z minus x would be negative 3 over the square root of 6. Okay, so 2 possibilities there. Okay, it depends on if we're trying to maximize or minimize it, right? So our original function was 3x minus y minus 3z. So f of negative 2 root 6 over root 6, 3 over root 6, 1 over root 6 would equal negative 6 over root 6 minus 3 over root 6 minus 3 over root 6. So it'd be negative 12 over root 6. We'll rationalize that. So negative 2 root 6. Okay, and then f of the opposites, right, will be 6 over root 6 plus 3 over root 6 plus 3 over root 6, which is going to be 2 root 6. Okay, so the maximum value would be 2 root 6. The minimum would be negative 2 root 6. Okay. All right, and we've got one more that I told you that we were going to do. So in the 11.7 video, we had find the maximum volume of a rectangular box that is inscribed in a sphere of radius r. Okay, so our primary, V is length times width times height. Okay, and remember we talked about how the length would be 2x, width would be 2y, and height would be 2z. So this would be 8xyz. Okay, and then your sphere, your secondary, x squared plus y squared plus z squared equals r squared, where r is a constant. Okay, so we went through the whole 11.7 method of solving it. Okay, and now we're going to do it with Lagrange multipliers. Okay, So our gradient of our primary equation would be 8yz, 8xz, 8xy, okay? And the gradient of our constraint would be 2x, 2y, 2z. So we've got our equations. 8yz equals 2 lambda x, 8xz equals 2 lambda y, and 8xy equals 2 lambda z. Okay, so we can scale them down. And we're going to have 4yz equals lambda x, 4xz equals lambda y, and 4xy equals lambda z. Okay, and then we also again have the x squared plus y squared plus z squared equals r squared. Okay, all right, I'm going to take this first guy and rearrange it. So 4z equals lambda x over y. And then I'm going to plug it into this one for 4z. So 4z times x. So lambda x squared over y equals lambda y. So x squared equals y squared. Okay, so basically positive negative x equals positive negative y, right? Okay, now I'm going to do something similar. Okay, I'm going to take this one and solve it for, what did I do? I think I did 4x. 4x is lambda y over z, and now I'm going to plug it into this one. So 4 lambda y squared over z equals lambda z. Oops, not 4, sorry. Y. In place of 4x, I put the lambda y, so no 4. Okay, so then I would have lambda squared equals z squared. I'm sorry, y squared equals z squared. Okay, so then positive negative y equals positive negative z. And we knew that was coming because we did it in another video. Okay. And again, we're squaring everything, so it doesn't really matter if we choose the positive or negative combinations. Like this will give you the corners of your box, right? Your 8 corners. There's 8 different ways we can arrange the positive and negative y's and z's, okay? And x's, y's, and z's. This will give us 8 points, okay? Doesn't really matter. But since they're all the same, then x squared plus x squared plus x squared equals r squared. 3x squared equals r squared. X squared equals r squared over 3. So x is r over the square root of 3. That's also y. That's also z. So the volume is 8 r over the square root of 3 cubed, okay, which is 8 r cubed over 3 root 3, which is what we found yesterday, or the other day. Okay. All right. So there's a bunch of examples for you. This is not an easy section, so definitely do your best with it. And like I said, practice additional examples if you feel like you need them, and we will go over them in class too.